will be looking into temperature changes, and you will be investigating the variables that affect temperature changes in reacting solutions, such as acids plus metals, acids plus carbonates, neutralizations or displacements of metals. Now we're going to be looking at a neutralization today, and the first thing you'll notice is I am wearing big full face goggles. Now this is because we are going to be using sodium hydroxide solution, which is quite dangerous to yourselves. So always make sure you are wearing your full face goggles. I have a beaker which has been filled with a polystyrene cup, and I have pre-measured 8 volumes of 5 centimeter cubed sodium hydroxide. Now that's going to save me time later in the practical, because this is one where you have to make sure your timings are as good as possible. I've also pre-measured 50 centimeters cubed of hydrochloric acid for this practical. Now, standing the polystyrene cup in the beaker makes it a bit more stable, but it also adds a little bit of insulation because we're going to be looking at a change in temperature. So we want to minimize the heat being lost from any other sources as best as possible. I've also included a lid for my thermometer to try and add that extra layer of insulation for my practical. I'm going to add my 50 centimeter cubed hydrochloric acid into my polystyrene cup. I'm going to place my thermometer very gently, making sure I don't rip a hole in the bottom. I'm just going to wait for that thermometer to get up to the appropriate temperature. Some students will take the measurement as soon as the thermometer has gone in. That's not going to be very accurate. It's going to affect your results. It's going to make your results potentially unreliable. So give that thermometer time to get up to temperature. We would expect the starting solution to be around room temperature, but we cannot make any assumptions. Right, when I have given my thermometer time to reach temperature, I'm going to pull this out, not taking it too far, and my starting solution is 19 degrees Celsius. Now, very quickly, I'm going to put that back in, being sure not to rip a hole in the bottom of my polystyrene cup. Here I have pre-drawn a graph with all of the volumes of sodium hydroxide we will be adding. Now, you'll notice the first one says 0. This is our starting temperature. We've included our units at the top, so we do not need to include the units on every individual row. So I'm just going to put 19. That's my starting temperature. Now, this is where the timing comes into play. Each time we are going to add 5 centimeters cubed of sodium hydroxide. This is an exothermic reaction, so energy is going to be released as they are reacting in this neutralization. Very important that each time we add the sodium hydroxide, we replace the lid to keep any heat in the solution. Now, when we add the solution, we're going to wait for the thermometer to stop rising. So let's add in our first volume of sodium hydroxide. Now I'm going to move the lid to the side, pour this in, tap it to make sure everything has been released, and replace the thermometer in. Give it a little stir to make sure that it is reacting as quickly as possible and everything is reacting. Be careful each time to stir for roughly the same amount. That is one of our control variables. Now, I'm going to give it a few seconds to react. I'm going to lift it, check my temperature, place it back in. Just to be certain, I'm going to give it a few more seconds and see if that is still increasing. We want the point where it is no longer increasing. This means all of our sodium hydroxide has been used up, but we have an excess of hydrochloric acid. Check that one more time, and it is still at 24 degrees. So I'm going to write down 24, and I'm going to add my next cylinder of sodium hydroxide solution. Tap it, place that back in, stir it again, roughly the same amount, give it some time to react. Now, each time we're not going to add the next cylinder of sodium hydroxide until we are certain the temperature is no longer rising. However, we don't want to leave it too long as it may start to cool. But this insulation is going to help give us a bigger window to measure and add our next solution. So once again, check the temperature change. It's gone up to 25 degrees now. So I'm going to write down 25, and then I'm going to add my next bit of sodium hydroxide, continuing until we have added a total of 40 centimetres cubed sodium hydroxide.
Now, after we've done this experiment, we would repeat it again, and if possible, again. So we'd have 3 clear experiments and 3 clear pieces of data. Once we've got that, we would calculate the mean. We would also look for anomalies. If we had an outlier or an anomaly, we wouldn't include it in our mean, okay? For time's sake, we've only done 1 experiment here, but you do it 3 times and find the mean. Now, I'm just going to plot this on a graph. Remember, the independent variable, the thing we change, is on the x-axis, and the thing we're measuring is on the y-axis, because the measuring is the dependent, and what we're changing is the independent. So I've just roughly plotting them, started at 19, so clearly it will go slightly up, then it will go slightly up again, until it's reached its maximum temperature. Then it will start to go down. Now I'm drawing these quite roughly, okay, so we'll have 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? So what I've done on there is quite rough, okay? Now clearly I've done that because we don't have a graph board, but in your, on your graph paper, yours would be, well, I hope, accurate. In your mark schemes, you tend to get like 1 mini square away before you start to lose marks. So it would be worth checking to make sure you're accurate. Now, you could, if you saw that in an exam, draw a curve, but because it's 2 clear things that are happening, they want you to have 2 clear lines of best fit. Clearly, the first line of best fit is going to be increasing, and the second line of best fit is going to be decreasing. Okay, so you would get your ruler. You do not go through every point. Using a ruler, I'm going to roughly, okay, draw a line of best fit. So something like that. Now notice here, it hasn't gone through every point, but it is showing the trend. And I could have done it slightly higher, as long as it's looking right. That's where you get your marks. And then again, I'll do a line of best fit going down. Again, you could change that line of best fit and have it going through more points, but it's difficult to do on the board, easier to do on your graph paper. Now, what you'll notice here is you've got a trend that's increasing. That is because it is an exothermic reaction. It is giving out heat. So therefore the temperature is increasing. However, at roughly this point, it starts to decrease. That is because it's no longer doing its reaction. It's no longer producing heat. So just like everything, it will start to cool. So we've got exothermic reaction. Here, it's finished doing its reaction, so it starts to cool. And I mean, this relates to then the physics practical thermal insulation. Now, this is a graph for an exothermic reaction, and we would have a title of it. We would have a title using these 2 parts of my table. So we would say a line graph showing the total volume of sodium hydroxide added and its maximum temperature. Now this is a exothermic reaction. If it was endothermic, it would kind of do the opposite, okay? Because the first bit would be the endothermic reaction, then when it finishes all its reaction, it would start to heat up back up to room temperature, okay? Now, because often you're asked to do predictions on graphs, it's often worth extrapolating these lines to go a little bit further. And on your graph paper, that would really help when coming to make predictions, okay? So for instance, if I was predicting it. However, remember that it's not going to go lower than room temperature, because things don't cool down lower than room temperature unless it's an endothermic reaction. Also worth noticing, if I put more insulation around this, as we do in the physics practical, this line wouldn't cool down as fast, so it would be a shallower line. And if we didn't have insulation around it, it should cool down much faster, so it'd be a steeper line.